Welcome everyone. I'm Tony Waskilly and I'm a Professor of Energy Systems and Co-Director of Durham Energy Institute at Durham University. This is the second day of our 4-day Net Zero Research Conference. The first 2 days of this conference are structured around the themes of Network H2, that's the Network for Hydrogen Field Transportation, which is funded by EPSRC and led by myself at Durham University. The network brings together researchers, companies, governments, and other stakeholders across the UK and interacts with internationally leading organizations and researchers across many different countries in the transport field. The structure of the network is around 8 cross-cutting themes. Firstly, on whole transport and energy systems and the interaction between them, pathways to sustainable hydrogen production and its distribution, compact and lightweight hydrogen storage, and more compact and lightweight onboard hydrogen energy conversion devices. Also on improved lightweighting and efficiency of electrified powertrains for transport applications, hydrogen compatibility of materials and their safety. And the final 2 themes are on multimodal transport, logistics and autonomy, and policy, economics and societal impact. So EPSRC funds this national network, as I mentioned, and has been awarded to us to allow us to act as a forum to maximize impact from the research that they fund and the research that UKRI fund, and to communicate and share best practice and disseminate information and data all around the theme of hydrogen field transportation, and that's all transport modes. Also to capture state-of-the-art and identify the research challenges from that exercise and examine ways to incentivize and look at the barriers that exist to the take-up of hydrogen for transport. We also have 50% of our funding to support new research programs, so funding cross-cutting projects to unlock research on hydrogen transport applications. Also, we aim to provide a wider forum for all stakeholders, again, for all modes of transport and technology developers, and to foster long-term collaborations between outstanding international research teams. And finally, to engage with the wider research community across the physical sciences, social sciences, and engineering disciplines to maximize dissemination and impact of the research outcomes, and to stimulate knowledge transfer between academia, industry, government, and other stakeholders. So over the 2 days, we are looking at the challenges across different forms of transport, as well as developing the supply chain to support this hydrogen transition. So today is organized in 3 parts. And we're moving now into covering storage and end use of hydrogen. So let me introduce our first speaker this afternoon. So it's Professor David Grant. David leads the Advanced Materials Research Group and the Beacon on Propulsion Futures at the University of Nottingham. He conducts research on the hydrogen storage, the storage of hydrogen, and of thermal energy, and also does research on biomaterials for surface modification, coatings, nanocomposite structures, and degradable materials. So, David, over to you.
Welcome everybody. Thank you for inviting me and spending the time with me for the next 20 minutes. I hopefully got a little bit for everybody on here. So I'm going to cover quite a wide range. So first off, I'm going to talk about hydrogen in the region. So for example, this morning we talked, it's really interesting talks about how the hydrogen could be used, produced, and East Midlands, where I work, Nottingham, is a classic inland city. So we're not going to get the hydrogen directly from renewables. Most of the hydrogen centres are around the coast. We're going to have to pipe it in, as we heard earlier today, or generate it on site with electrolyzers. And of course, what we do have is good electrical connectivity, because we've got all the old power stations down the Trent, which can be converted if that's necessary. And we're obviously being in the Midlands, we've got the largest freight transport, air freight transport in Europe, as well as road and rail. So hydrogen transport has obviously an important part of the mix in what can be used for. And so we're not sitting on top of a large hydrogen cavern, a salt cavern. So hydrogen storage is an important part of the whole process, from whether it's generation, distribution, storage, usage and conversion into other fuels, synthetic fuels and ammonia. So as by way of reminding everybody, hydrogen itself is got a great gravimetric density, so it's like 3 times that of diesel or gasoline. But of course, volumetrically, it's a bit more tricky to contain and keep the size down. And so, if you look at the different methods of which you can store hydrogen, you can either compress it, you can liquefy it. I've got a pointer here. Highlighter, there we go. So you can liquefy it. You can store it in a solid state store. Or you can store it in a porous material by physisorption process. Now, compression and liquefaction you probably know quite a lot about. The chemically storing it has a lot of advantages, and I just wanted to explain a little bit about some of the areas that it might have an impact. So if we take these materials and present it on a different graph, and on this graph here, you can see that on the top right hand side we've got diesel and petrol, but obviously liquid hydrogen is 3 times that in terms of energy density, energy per unit mass. But of course, in terms of energy density, energy per unit volume, it's a lot lower. And so there's an interest around whether the liquid hydrogen tanks are sufficient for certain types of transport, particularly in aircraft. And so this is not a new concept. This has been around for a while. So if you take, there's a paper over 10 years old now, where you look at a regional aircraft, and you can see that the fuel mass that you require for a particular journeys are roughly 35% of the kerosene. But of course, you've got to store the hydrogen, and you've got to, if it's in the liquid state, you're going to have to redesign the aircraft completely and extend it, in particular, to accommodate that extra volume. But actually, in terms of the overall takeoff weight, it's actually slightly less, although the landing weight, because of all the infrastructure, makes it more. So it comes down to cost, and it comes down to modification, and so there is places for liquid hydrogen, not just for transporting it around the world. Let's go back to that graph again and say, well, hang on a minute, we can't use liquid hydrogen for other forms of transport. The cost and the technology to put it into vehicles is quite a lot. What about these what about trying something else like these light elements or metal hydrides? You can see that they actually have a better volumetric density than liquid hydrogen, so that makes a lot of sense. But of course, gravimetrically, in terms of their energy density per unit mass, they're a lot less. Okay, and in particular, the conventional metal hydrides around room that operate around room temperature are quite low in specific energy, and so that would make the tanks a lot heavier than currently, but they are still several orders, almost an order of magnitude larger than better than battery technology. It's just that they are still too heavy, and so you can see the long way batteries have to go to get anywhere, really, for some of the transport, long distance transport applications in particular. So let's just look at that a bit. So these complex hydrides, which have these attractive energy densities in here, these of light elements tend to be complex hydrogens. Why aren't they being used at the moment? Well, the problem is that you can have a very good weight percentage per unit mass. So, for example, the DOE and the States look at 7 weight % being a reasonable sort of number. 7 weight % of your tank essentially is hydrogen, and if you compare that with compressed gas, you'd talk about 4 or 5 weight % of the tank is actual hydrogen. These materials up here are like lithium borohydride is 18%. So you can see the extreme excitement that was done about 10 years ago, or actually close to 15, when these first became investigated for potential stores. But you can immediately see the problem is that to release the hydrogen, you have to go up to 300 and 400 degrees. And so a lot of research has been looking at trying to get these complex hydrides to drop in temperature so that it can be used. Otherwise, you're using about 1/3 of the fuel to heat the tank up to release the hydrogen. The other problem with them is, of course, they're difficult to reverse. Some of them are reasonable to reverse, but some are less so. And so we want to work in this sweet spot around here. And this is here we've got the weight %, as I said before, and if you go to physisorption, well, you get some decent capacities, but you have to go down to liquid nitrogen temperatures, and they also have very large volumes, so we're not so interested about that. And just to show you how that would work, with these, this is lithium borohydride, which has got various additives put in it. This one happens to have a magnesium additive to it, and what you can do is reduce the temperature from here down to 350 to release the hydrogen, but it's still way too high. So the research is still ongoing to find that ultimate material. So for the moment, the cost-effective ones are these cheap metal hydrides. Magnesium hydride has got a weight % of 7 weight %, but the trouble with magnesium hydride is you have to heat it up to 300 degrees to release it. So we're interested in metal hydrides that operate at room temperature, because there's no net problem in releasing them. And of course, the advantage of these hydrides is that they store hydrogen at a few bar. So what you do is you take some stationary store, in this case, and instead of having a compressed gas, you could replace it with a very small tank on the right-hand side, and you'd have the same amount of hydrogen stored in that kind of scenario. And this is what we've been doing here. It's an exothermic endothermic reaction, so you have to make sure the heat throughout the bed works, and so that's one of the design challenges for these, but these are not insurmountable, and in fact we've done a lot of work with UK Innovate projects delivering that. The other challenge is to try and make the material take up more hydrogen. As I say, the metal hydrides take up to about 2 weight %. If we could get that to maybe 4 weight %, or even 3, then it becomes very interesting indeed. And so to show you, these are the types of sites that we look in the material to find the increase the capacity. So often we look at expanding the lattice of the structure. This is an AB2 alloy. These two elements are the A site, that's the B site. And essentially by modifying them, we can get a situation where we can take up and hit more hydrogen. So here along the x-axis, you've got the weight percent hydrogen. And so you can see in this alloy here, we only have at 1.6 while here we can almost get up to 2.8%. So you can see the attractiveness of that. Now, at Nottingham, we've been trying to replace these hydrides, which have vanadium in them, with ones which don't have vanadium in. And that's meant that we have a cost reduction of about a factor 5. So in terms of the material, we've dropped it from about £50 per kilo to roughly around £9 a kilo. And this starts to make sense for stationary stores. We heard this morning that there's a need to store hydrogen locally and safely around locations. And of course, as you can see from this graph, you can store hydrogen at modest pressures, 5 bar or 10 bar, and you can tune that pressure, and then you can release it into a fuel cell without having to use a regulator or anything like that. So there's a lot of interest in these kinds of systems. And so in terms of research, we're now looking at artificial intelligence and machine learning to develop new materials, and this is where the current research is developing. So let's go back to the transport again. So for road and rail, let's consider a compressed gas hydrogen refueler. So we've got a hydrogen refueler at Nottingham, a test bed there, and of course you probably recognise the Alstom hydrogen train. Of course that's got compressed gas in it, so that needs a significant volume. Remember, it's about 4 to 5 weight % of the hydrogen in a compressed gas tank in terms of its weight, and volumetrically it's much inferior to metal hydride stores. And so imagine you have a refueling station, and you're close to other houses or other places. We started to look at some modelling around what would it be if we took the buffer tank that's used in these electrolyzers. This is with a UK Innovate project. Could we replace the buffer tank with a metal hydride tank, and what effect that would have? And essentially, it means you can refuel maybe 25 times more vehicles, because the space that you've got is considerably reduced because of this volumetric energy density of metal hydrides is so much superior. The other application of these types of systems are the challenges around compression. So as you probably know, compressing hydrogen is quite difficult, and if you've got a small scale compressor, you've got to run it and maintain it, and the seals often go, and it's difficult and expensive. The capex cost is high, instead of which you can replace it with 2 metal hydrides. And so what you do is this is your temperature along here. This is 1 over temperature, so this is low temperature, so this is about room temperature. You take your metal hydride, you fill it up with hydrogen, you then heat it, and as you heat it, the pressure goes up because of the thermodynamics of the system. The pressure will go up, so this will go up to about 40 bar, and then what you do is you open a valve and you put it into another tank, into this tank here, and that's now at room temperature. You transfer the heat from one vessel to the other, and then you heat that one up, and that's now at 300 bar, and so on. And so it's a great way of compressing gas without having to use a lot of energy and very few moving parts. The only moving parts you'd have would be a valve opening and shutting. So this is part of a project that we're working on as well. All right, and so I've covered air, road, rail. What about marine? Well, marine, as you may know, there's a lot of interest in using ammonia for marine. And of course, the flame temperature of ammonia is quite slow and lower temperature. So one suggestion is to prevent NOx forming, that you'd have the high flame speed that hydrogen gives you, and this, putting a pilot into flame into that system can produce a more efficient system, and one of our colleagues at Nottingham is looking at this. The other interesting thing about metal hydrides, and we're developing a system, is that when you release hydrogen from a metal hydride, it's an endothermic reaction. And so if you have a metal hydride tank in a HGV truck, which is requiring cooling, such as like for refrigeration, such as locally we've got Blackwells and other companies that distribute food in chilled vehicles, then the fuel store actually can be used for chilling the vehicle itself. And so this is another potential interest around that. The other way is you can reverse it and move hydrogen around, so you don't actually lose hydrogen in a loop, and you use an endothermic exothermic reaction by moving hydrogen in to maintain temperature. And again, taking the internal combustion engine for a marine application, one of the big challenges is as we move into ships moving into ports, is that when they're moving in at low speed and the engine's not very hot, the emissions from that is very, very bad indeed. So the very worst scenario is that the ships are reasonably polluting when they're out at sea, but when they get into port, they're even more polluting. So actually, while it's out at sea, you can have you can dehydrogenate a store and use it for chilling on the boat, and then when you come into port, you can then recombine the hydrogen in this loop here. When it recombines, it gives off heat and can be used to keep the engine at the right temperature while it's idling in port. So there's lots of applications around hydrogen. I've kind of rattled through them all. I just want to finish by saying that we've got a great demonstration facility here at Nottingham, and welcome anybody who wishes to come and use. We've got a 20 kilowatt, a 200 kilowatt electrolyzer. We're feeding in buildings next door. For example, we've got a brand new power electronics building, which is the largest power electronics group in the world, I'm told, and we're delivering hydrogen stores into fuel cells and then into electric motors and drives. So they've got a test capacity of 20 megawatt test facility. It's amazing test facility they've got there. So we've got some really interesting stuff, and if you're interested in any of that, or the Hydrogen Innovation Zone in the East Midlands, we'd be really interested to hear from you, and thank you for your time.
Yeah, thanks very much, David, for interesting presentation on storage and the options and the facilities there and capability at Nottingham. We'll move to the second presentation. It's going to be given by Professor Nigel Brandon from Imperial College London. Nigel is Dean of the Faculty of Engineering at Imperial College. His research is on electrochemical devices for low carbon energy applications, with a particular focus on fuel cells, electrolyzers and batteries. He is director of the UK Hydrogen and Fuel Cell Supergen and chair of the Sustainable Gas Institute at Imperial. Nigel is also a founder of Carez Power fuel cell company and RFC Power, a flow battery company. So over to you, Nigel.
Well, thanks for the kind introduction. I'm going to try and, a bit like David, sort of give a broad overview really around hydrogen fuel cells for transport applications, touch a little bit on some of the issues around fuel cells in brief, and then an overview of where the sort of technology is today, and then we're happy to take any questions. As you kindly mentioned in your introduction, I'm a director of the Hydrogen and Fuel Cell Supergen, which is, as I'm sure many of you know, one of the Research Council's investments in the energy space. And we specialize in hydrogen and we specialize in fuel cells. And there's a web link at the end of this presentation, or you can find it, I'm sure, relatively straightforwardly if you want to see the sorts of things the hub is up to. And as you also mentioned, I'm chair of the Sustainable Gas Institute. This is a largely industry-funded program looking at all aspects of gas and gaseous fuels, but it has a particular focus on hydrogen and the role of gas and gaseous fuels in the low carbon transition. So today we're talking about transport, and I'm sure has been mentioned in other talks, and I'll mention it as well. Of course, hydrogen has a multiplicity of roles it can play, not only in transport, and the cross-sector coupling that we might get with hydrogen will be important. But this is why it matters for transport. There's a carbon focus, and that's obviously very strong and really has brought hydrogen back onto the map as far as policymakers are concerned. But air quality matters as well, and this is a little bit old, but I think it's a nice picture that's showing NOx emissions in London, and the brighter the red, the higher the level. And this is Heathrow back in the day when we used to get on aeroplanes and fly places. But these are the main arterial routes in and through a big city like London, and it's indicative of the impact of transport emissions, not only on carbon, but on local air quality. And again, just to remind ourselves, because it matters, whilst we're talking today about hydrogen for transport, that is going to be very strongly coupled to hydrogen production, distribution, and end use in other sectors as well, not the least of which in driving the price and cost of the hydrogen we're going to put into that vehicle. So I'm sure you talked about that earlier today. Sorry I couldn't be with you, but it sort of reinforces the point that this is a system piece. Whilst we're going to focus in this talk on the vehicle and the powertrain of that vehicle, the issue around the hydrogen distribution system and production method, of course, is very important. So let's talk a little bit about fuel cells. I'm going to concentrate on fuel cells as the energy conversion device for hydrogen. It is certainly the case that you can put hydrogen into heat engines, particularly for large-scale gas turbines, and there are certainly very serious companies involved in producing hydrogen turbines today. But I'm going to talk about fuel cells because if we're going to put our hydrogen into a vehicle that's not a very large vehicle, so for example, a car or a bus or a truck, mostly these are not going to be gas, and you've got to be very large before it becomes a gas turbine. So for transport applications, with the possible exception of air, fuel cells, I think, are the rational choice. They give you a high electrical or conversion efficiency, and that's one of their key attributes. So this is my sort of 101 slide for what a fuel cell is and how a fuel cell works, and just to remind ourselves what that is. So these are electrochemical devices. They work by putting in a fuel on one side, and let's look here at the PEM on the right-hand side, the PEM fuel cell, the polymer electrolyte membrane fuel cell. That's the most common type found in transport applications. In this particular device, we have an electrolyte, which in this case is a proton conductor. And that electrolyte has on both sides electrodes, which drive the electrochemical reactions, the charge transfer reactions. In the case of a PEM fuel cell, excuse me, it needs a high purity hydrogen feedstock. And it needs to be high purity because there are catalytic materials, which are platinum group metals. We'll look at those in a bit more detail in a moment on the anode side here. And they are deactivated by contaminants in the hydrogen, like carbon monoxide. So we have to be careful about the hydrogen purity. So we want high purity hydrogen on the fuel side. On the air side, then we have oxygen as our oxidant, normally, in fact, in all these applications from air. And on the hydrogen side, we are releasing electrons, we're forming protons, and those protons are being transported across the membrane where they combine with the oxygen molecule, plus electrons, the electrons being carried around an external circuit, that flow of electrons being, of course, current. And we generate a voltage, which is coupled to the Gibbs energy of reaction to the thermodynamics of the overall reaction of hydrogen plus oxygen produces water. We do produce water on the air side, and that's an important engineering challenge because water can flood electrodes and block the ingress of oxygen in air, and that's a challenge when that happens. So a PEM fuel cell runs at about somewhere between 80 and 100 degrees centigrade. and is the most common type found in transport applications. And that's because they have a high power density relative to the other fuel cell types. So they are more readily accommodated in the tight space that's available in certainly light duty vehicles. As we come towards larger and larger vehicles like trains and ships, as David's just sort of introduced from the hydrogen storage side, we might start to think about a wider range of fuel cell types. I am going to briefly mention towards the end of my talk also solid oxide fuel cells. That's the cartoon on the left here. Same overall principle. We have air, oxygen from air on the cathode. We have a hydrogen or a hydrogen-rich gas on the anode. Solid oxide fuel cells run at somewhere between 600 and 800 degrees centigrade. And at those temperatures can treat a wide range of fuels as an effective fuel for the fuel cell. They don't need high purity hydrogen. They can put in, for example, carbon monoxide and other fuels that you might get in blue hydrogen, or pick up in gas pipelines when you're distributing that hydrogen. So they're more fuel purity tolerant. They have now an oxide ion conducting membrane. So oxygen on the air side is reduced. The oxide ions transported across the membrane, which is a ceramic material. Conventionally an yttria-stabilized zirconia, but other materials are also used, where those oxygen ions then combine with the fuel, in this case shown as hydrogen, to produce water, in this case steam, because the temperatures are such that this is all in the gas phase. So this is a high temperature device. It's not being developed as a prime mover for transport applications, for example, for cars and trucks and buses, though there is a program that is being developed in China with the company that Tony mentioned that I was involved in helping set up, Ceres Power, and that's looking at putting this technology into buses in China as the auxiliary power unit, not the prime mover. Okay, so that's our little picture of how a fuel cell works, and some of the kind of a little bit of the fundamentals. If we go and focus now on the PEM fuel cell, because that's the one that's most relevant to most transport applications. This is a little cartoon showing our PEM fuel cell in a bit more detail. On the anode side here, then, we have our hydrogen side. We have a bipolar plate, so that's the plate that will connect one fuel cell to another because they're connected in electrical series to step up the voltage and hence step up the power. We have a porous gas diffusion layer, which allows our hydrogen ingress into the catalytically active region. In practice, this gas diffusion layer will be thicker than this catalytic layer. The catalytic layer is a mixture of carbon, PTFE, and catalytic material, which are generally platinum or platinum group metal catalysts, very high surface area materials. And this is where the charge transfer reaction happens. We then have protons produced. Those protons are transported across the membrane. They will take with them water molecules by electroosmotic drag. And at the air side, they will combine with oxygen coming in again through a gas diffusion layer and into the catalytically active region to produce liquid water. So you can see you get a buildup of liquid water on the air side. And that water, if not properly managed, will pool in these porous layers and then, of course, stop the access of oxygen from air to the active sites, and the fuel cell will not work well at all. So this sort of mass transport constraint and engineering solutions to that is actually a very big practical problem, and one in which people have spent a lot of time and effort to engineer the emission of that water to stop flooding. There is some water transport back across the membrane by down a concentration gradient, so you do get some back pressure, backflow of water down that pressure gradient, but essentially the buildup of water is on the air side over time, coupled, which is very strongly related to the current density. The higher the current density, the harder it is to prevent that flooding problem. So water management in a PEM fuel cell is very important, and it has a big engineering implication. We have the membrane itself will only function effectively when properly hydrated. So we need to keep the right humidity on both sides of the membrane. On the anode side, because we're pulling water across with the flow of protons, despite the back diffusion, we have a net water loss from the fuel side to the air side. And on the air side, we have a water buildup. So we can get dehydration on the anode side of the membrane and loss of conductivity and flooding on the air side. So water management is an important practical challenge in as we scale up from a cell to a stack. So if we look at a cartoon of a stack, as I say, a fuel cell stack, which produces something like a useful output for a vehicle, like a 50, 100 or 150 kilowatt stack for your electric vehicle, is comprised of many individual cells, each cell under operating conditions producing around 0.7 volts, producing just over a volt at open circuit when no current is being drawn. We have these MEAs, which are these membrane electrode assemblies. This is the gas diffusion layer coupled with the catalytic layer in the electrolyte, and they are separated by these bipolar plates or these interconnect plates, which distribute the fuel and air and are also part of the thermal management system. Fuel cells are exothermic devices. So again, if we're up at perhaps a power density of 3 or 4 kilowatts a litre, then we also have to manage heat, given that at that point it's probably about 60% efficient. We also have to manage 2 to 3 kilowatts per litre of heat from the device. So the higher pressure, the higher power stacks are going to be liquid cooled. Lower power stacks may be air cooled, but for a lot of vehicle applications, we're dealing with higher power stacks, and so we're dealing with liquid cooling. That stack has to sit in a system, and this is a sort of generic flow sheet for a PEM fuel cell system. Just to make the point that it's not all about the stack, you also need to think about how you're going to do this humidification system. You're going to think about how you're going to put air through this, either as the oxidant, for example, or in some cases as the coolant, but most likely as the oxidant. So you've got some form of air compressor or air blower. You've got some form of water management system. You've got to put your hydrogen through and humidify that and recuperate water, for example, and re-inject it. So there's quite, and obviously you've got to thermally manage the stack itself via some form of radiator. So all of these components are important. Obviously, you also have to have some form of power electronics, and the fuel cell itself is likely to sit inside some form of hybrid system alongside a battery. And of course, as David has just explained, very importantly, alongside the hydrogen storage system as well. So this is a little bit old, but it's some real data showing the efficiency power curve for a fuel cell stack. And the blue curve here is experimental data on this particular stack. And as we see with all electrochemical devices, as we draw power from the stack, the efficiency goes down. As to say, we draw power, the voltage goes down, the efficiency goes down. But importantly for a vehicle, as we take power away, as we go to part load, the efficiency goes up. So the blue is the stack efficiency. Now the green is the system efficiency, which of course is lower than the stack. And that's because if we flick back to here, we can see we've got a number of components like pumps, compressors, all of which have an electrical power requirement delivered by the fuel cell. So as we go down and down and down, as we go down in power, the efficiency at the system level will go up until it gets to a point at which you're simply servicing the balance of plant components. And then the efficiency will start to fall down as we hit the parasitic loads on the system. But across most of the drive cycle for a vehicle, unlike a heat engine, which tends to have a rather peaky efficiency power curve, a fuel cell efficiency will go up as we go to part load. So in real driving cycles, this is a very attractive characteristic to give us overall improvements in fuel economy. So this is a cartoon of the sorts of layout you might see in a vehicle with obviously the thermal management system, a radiator at the front of the vehicle here, DC-DC converters, in electric motors, similar to find you have in a battery electric vehicle, of course, your fuel tanks. In this case, this would almost certainly be a high pressure compressed hydrogen system, a battery pack, because you need to have a battery for fast startup, but also for a regenerative braking on the vehicle, the fuel cell stack. And this is very similar, and I suspect it's based on the layout of the Mirai, for example. So where are the technologies today? And I think John, if I might have spotted John Hunt's name in the room. So John, thank you again for your support. This is the Toyota Mirai that we have at Imperial College. Toyota very kindly made available a number of hydrogen fuel cell Mirais around a number of academic institutions, including ours. And we're very grateful for it, and I enjoy driving it, and it gives us a good opportunity to experience what an actual hydrogen fuel cell car is like. It's very convenient and nice to drive. It's not so super convenient to refuel, and indeed we don't have a huge amount of choice, but we do have choice in London. There are about 4 or 5 actually now relatively convenient places we can go and refuel this car. But you know, the landscape on hydrogen fuel cell light duty vehicles is growing. It's an area where in fact the hydrogen fuel cell vehicle is going, you know, pretty much head to head with the battery electric vehicle. And there, you know, we happily discuss that in the Q&A perhaps about the relative merits. But it's certainly the case that this is an electric car that you can refuel in a few minutes and do, you know, 300 to 400 miles in. And that has a whole bunch of advantages. Toyota brought out a new Mirai, and of course we also have the Hyundai fuel cell Nexo, and so there's some interesting vehicles emerging in the hydrogen fuel cell car space. You are of course into this debate about the hydrogen refueling infrastructure, and it is important that you develop both the vehicle fleet and the refueling infrastructure at the same time. If we move away from cars and we move into heavy duty vehicles, I think there is really no debate in my mind and in the mind of many others that this is a clear sweet spot for hydrogen fuel cell electric compared to battery electric. As the amount of energy you need to carry on the vehicle goes up, the benefit of having a hydrogen fuel tank becomes increasingly marked. So for buses and some of the other applications I'm going to discuss, there's a huge amount of emerging interest in hydrogen fuel cell electric. This is a UK program here, and I think again, I saw Alcoa mentioned on one of David's slides. So Alcoa are a UK fuel cell integrator working with Optare to launch this hydrogen fuel cell double-decker bus. And in London, we've had these European trial, effectively buses driving around for a number of years now. And of course, they're also in other cities now in the UK. If we move away from buses into trains, and David also showed this photograph of the Breeze hydrogen fuel cell battery hybrid system, which has been built by Alstom and Evershot Rail for the UK. And also we have this University of Birmingham and others, Hydroflex hydrogen fuel cell electric train on test. So this is a really interesting market that I've worked in fuel cells a long time, and there was a lot, you know, a number of years ago, we wouldn't have foreseen hydrogen fuel cell being developed for the, or foreseen it for the train market. But this is to replace diesel on the sorts of suburban, largely lines that are too expensive to justify electrification by overhead cable, for example, but where you can think about electrifying with a hydrogen fuel cell. And a number of these are now running in Germany and Austria, showing very good performance, and we're starting to evaluate them here in the UK. If we move again then into trucks and off-road, again, a very clear opportunity. I don't think really that hydrogen is now competing with batteries. I think it's competing with synthetic fuels or e-fuels or biofuels. These are Hyundai trucks now been shipped over to Switzerland. Of course, in the UK, we have JCB looking at hydrogen-powered excavators. We've got Bosch talking about setting up hydrogen fuel cell powertrain manufacture, again for the truck sector. And then finally, just to mention, this is my own interest, because this is the company I helped set up along with a number of other colleagues, but is now working on solid oxide fuel cells. So this isn't a PEM. The picture in the top right here is a photograph of a Ceres solid oxide fuel cell stack. Looks a lot like a PEM, but it's a solid oxide technology designed to work at about 600 degrees centigrade. And that's being put into buses in China, not as the powertrain for the vehicle, but to provide the auxiliary power load and the heat for the vehicle, which can be run on hydrogen, but can also be run on things like LNG. So I'll stop there, open up for any questions, and just have briefly mention that there are some web sources of information for the Sustainable Gas Institute the Hydrogen and Fuel Cell Hub, and indeed our Electrochemical and Science and Engineering programme at Imperial College, if anyone wants to look in more detail. Thanks, Tony. We'll stop there.